Right, so today we want to do some actual examples for hypothesis testing, and our goal is to essentially see what types of claims we can either reject or fail to reject when it comes down to hypothesis testing. So last time we talked about what a hypothesis test was, and today we're actually going to do a few examples. So there are three main examples. There's population means, population proportions, and then the difference between means, or where you have two population means. So let's start out with a population mean. So imagine that a produce manager is told that the average diameter of an orange in a shipment is 2.3 inches. So you want the oranges to be a certain size, and the manager pretty much wants to ensure that the oranges are at least that big on average. Now some of them will be smaller, some of them will be larger, but the manager wants to know that the average size really is 2.3 inches. Or if it's larger, I'm sure the manager will be happy about that as well. So after sampling 100 oranges, he finds that the average is 2.27 inches. Assuming a level of significance of 0.05, and we'll talk about level of significance in just a second, we want to know if there's sufficient evidence to show that the claim is false, the claim being that the shipment of oranges is at least 2.3 inches. And the standard deviation is known to be 0.3 inches. So here's the idea when it comes down to actually trying to test this. And the idea is this. So we are given that the 2.3 inches, and we want to check to see whether or not it's really less than 2.3 inches. So what we're testing is we're testing our alternative hypothesis, essentially, that the mean is less than 2.3 inches. Because we want to know whether or not we can reject the claim that the mean is equal to 2.3 inches, but we want these to be opposite. So we're testing the claim that the mean is greater than or equal to 2.3 inches. Now the standard deviation is given to us. The standard deviation is equal to 0.3 inches. And the level of significance is this idea. The idea is that we were told that the average is 2.3 inches. But we took out a sample of 100 oranges, and we tested that sample and found an average of 2.27 inches. It is possible that the average size of our orange is in fact smaller than the average size of all oranges in the shipment, assuming that the shipment is really, really large. There is a probability that we could have grabbed a sample whose average is as low as 2.27 inches. So here's what we're going to do. We're going to say, okay, we have this normal distribution of sample means. The sample means we would expect based on the claim that it's 2.3 inches, it should be sitting with 2.3 in the center, and then it should spread out with the standard deviation of the sample means. So we get 2.27. It lands somewhere over here. We don't know exactly where. But we want to know that it's actually sitting in the bigger region. This would make us happy. But the question is then, what is the probability that I get something as low as 2.27, assuming that it's true that 2.3 inches is the average? So what I want to do is I want to calculate that area, because that would be my probability that I'm able to get what I got, assuming that it's true that it's 2.3 inches. This probability is called the p-value. So we call the p-value. The probability that we get the statistic that we got, assuming that the null hypothesis is true. And the level of significance is kind of like our breaking point. If the p-value is, the level of significance is the allowed probability. If it's lower than that, then the assumption is that the null hypothesis is false. So the level of significance is the allowed probability that we will allow something as low as that. Otherwise, we assume that the null hypothesis is false, and we reject that null hypothesis. So that level of significance is what we're going to actually compare it to, and we call this alpha. So we're going to check our p-value compared to alpha. If the p-value is less than alpha, so if the p-value, so the probability that this occurs, is less than alpha, the breaking point, then we will reject the null hypothesis. If the p-value is greater than or equal to alpha, we would fail to reject. So the idea here is that we want to know what's the probability. If the probability is so low, then it must be that the null hypothesis is false. So I want to continue on with this particular example. And in this particular example, again, the null hypothesis, which we should always claim, is that mu is greater than or equal to 2.3. The alternate hypothesis is mu is less than 2.3, and these should actually be complete opposites, and they are. The sigma for the population is given at 0.3, and that means that the sigma for the standard deviation for the distribution of sample means then must be equal to sigma divided by the square root of the number of people in my sample, which in this case is 100, so it's equal to 0.03. Now we got a statistic, an x bar, which is equal to 2.27, and we can actually calculate that area under the curve if we put 2.3 in the middle, and this is the distribution of sample means. Then 2.27 is actually exactly one standard deviation to the left, and we can actually calculate that in a second. So give me 2.27, and we want to find this area right here. That would be my p-value. So what do? I'm going to take my test statistic, which is my z-score, associated to my statistic from my sample, and divide it by the standard deviation for the distribution, and here we get -1. Now, if I look on the table, that -1 corresponds to a 0.1587 area under the curve. That's my p-value. Again, this is the probability that I got something as low as 2.7 or lower, assuming that the null hypothesis is true. So there's a 15.87% chance that I would have gotten 2.27 or lower, assuming that the actual average of the size of oranges is 2.3 inches. It's actually kind of, I mean, it's not likely, but it's not ridiculous to think that that occurred, given it's 15.87%. So this is not strong enough to reject that null hypothesis, because the null hypothesis could be true. There's only a 15.87% chance that it's that I would have gotten a sample like that, but that's still a decent enough probability. We compare that p-value, 0.1587. We compare it to alpha. It is greater than 0.05. This is my level of significance, or we also call that alpha. And for that reason, we fail to reject the null hypothesis. We can look back at the null hypothesis and say, oh, okay, the null hypothesis was that the mean is greater than or equal to 2.3. We fail to reject that, which means that that claim is possibly still true. If we had rejected it, then the claim is that would be we would be sufficiently have sufficient evidence to reject, if we were able to reject it, to say that it's not an average of 2.3 inches. But here we fail to reject. Doesn't mean that we necessarily accept it. Maybe it's still false, but we did not have sufficient evidence to actually reject that. The probability that we got that sample was high enough that we're not going to reject that null hypothesis. So this is the game. You start out with this distribution of sample means or distribution of sample proportions or so on and so forth. You get a test statistic, a z-score based on that. You find the p-value using the area under the curve. You compare that to your level of significance, and that tells you whether or not you reject or you fail to reject. So in this case, we fail to reject. Here's another example using population proportions. So it is possible that a candidate doesn't believe the actual voting count that comes in. And so if we have a vote for a candidate who's running for some office, it is possible that they are told that they got 46% of the votes, as in this case, and it's possible that the candidate believes it's false. So how would you prove that they didn't get 46% of the votes? Then you would run out and you would do a hypothesis test. In the hypothesis test, you could ask people who they actually voted for, and if you really got true answers from these people after the vote, you could compare that to the actual results. So if it's stated that 46% of voters voted for a particular candidate, and then you do a random sample of 1,000 voters, and 412 of them state that they voted for that candidate, you could check to see whether or not the claim that 46% of the voters is actually true. Now, in this particular example, it is not indicated whether or not we think it's greater than or smaller than 46%. So I'm going to do what's called a two-tail test. So we just don't believe it's 46%. So that means that we're trying to see if we can reject this claim that the proportion is equal to 0.46. And we would do that by looking to see if the alternative is true, that the proportion is not equal to 0.46. So in this case, we have a distribution of sample proportions. We're claimed that it's at 0.46 is sitting in the middle. And we want to look at whether or not if we land out on either side, far enough away from 0.46. Now we don't know whether it's bigger or smaller, so we're going to look at what's called a two-tailed test. Now, when we take our test statistic, in this case we have one because we get the 412. When we take this test statistic, we're actually landing over here. But we didn't know this before we actually went to go test it. So we want to say, not just that we landed over here, we want to also look at the possibility that we could have landed over here. Because all we're trying to test is whether or not it's not equal to 0.46. It could be more, it could be smaller. We didn't know this before we actually ran the test. So what we're going to do is we're going to take this area on the left-hand side and we're going to double it to allow that area to kind of also show up on the right-hand side. So that's what a two-tailed test will end up doing. So to run this two-tailed test, we need to look at the distribution. So here we're given, again, the null hypothesis is that P is equal to 0.46, and the alternative hypothesis is P is not equal to 0.46. We are given a test statistic. We're given a statistic, our P hat is equal to 412 over 1,000, which is equal to 0.412. And so that our test statistic then is our z-score for this distribution, which we're going to take 0.412, subtract 0.46. But then we have to divide by the standard deviation for the distribution. The distribution here is the distribution of sample proportions. So the standard deviation for the distribution of sample proportions is, according to the previous material that we talked about, would be equal to, well, we're given P as 0.46, so it would be 0.46 times 1 minus 0.46 all over 1,000, because that's the number of people in our sample. And then take square root of that, and we get 0.01576. Okay, so then we plug this in for our standard deviation of our distribution, 0.01576, and that gives us our z-score, and our z-score in this particular instance is equal to negative 3.04. So then we look that up on the table, and when we look that up on the table, we end up getting 0.0012. This tells us that in this distribution, this area right here is 0.0012, but remember we want to double that to look at a two-tailed. So our p-value is equal to 2 times 0.0012, that's equal to 0.0024. This is less than 0.01. That was our level of significance for this particular test. You're picking a probability that you want to check against before you actually run the test, and that's our level of significance. Since it's less, we reject the null hypothesis. So you reject the null hypothesis. The null hypothesis is equal to 0.46. For this particular candidate, though, it would not be that exciting because we're not only showing that it's not equal to 0.46, we'd be showing that it's less than 0.46, that it's 0.412 or something closer to that. Now, all we care is whether or not it's equal to 0.46 or not equal to 0.46. This is a strange example to do for this. What's more likely to do is something where you're really just trying to show something's not fair. In this particular instance, it's looking at a real proportion of voters, but where you might be looking for fair is if you get like a coin and you flip it, and you want to check to see whether or not it's landing heads more often or tails more often. Is it really a fair coin or is it weighted in a weird way? Or if you're rolling a die or something like that, you could check for fairness, and you really don't care if it's smaller or larger, you just care whether or not it's the claimed proportion of being fair, landing 50% of the time on heads or tails. But in this case, we can see an example where we can reject using that two-tailed test. The last example is when you want to compare two population means. So you play the exact same game. Where you want to compare means is usually when somebody's trying to say that they're better than someone else. So a car company maybe claims that their car gets better miles per gallon than their competitor. And in this case, they're saying, okay, so what do? We want to check that one mean is larger than the other mean. And I'll show you how to do that. Well, let's just say, so the first car company we would call the first mean, and the second car company we would call the second mean. And this hypothesis then is that mean one, when you take the first mean and subtract the second mean, they are trying to say that they are greater than the other. So that means that their mean would be larger than the other mean. This would be our null hypothesis, the thing that we're trying to test, which means our alternative hypothesis would be the direct opposite, mu 1 minus mu 2 is less than or equal to 0. So you're going to do this with some test statistics and so on and so forth. The big thing that we need to use here is we need to use the standard deviation of the distribution. There is a distribution of the difference of means, and that difference would have the mu1 minus mu2 sitting in the middle. And the standard deviation for this distribution of means, well, now you're actually taking the statistics, is equal to the square root of the first standard deviation squared over the first number plus the second standard deviation squared over the second number. Now these are the numbers of well, in this case, cars in the sample or number of people in the sample. You cannot guarantee that the samples are going to be the same size. Even if you think that they're going to be the same size, maybe you have some non-responders or something like that. So in this case, you have to really take that into account. So let's do this example. It's the same exact type of idea. So here we need a test statistic. So we got that it was 23.3. So x1 bar minus x2 bar is equal to 23.3 minus 23.2, which is equal to 0.1. We want to compare this against the actual population mean. So we're going to take that 0.1 minus, remember that the null hypothesis is that mean 1 minus mean 2 is greater than 0. So we want to check it against the 0. We want to divide that by the standard deviation of the difference of statistics, or sample means. Remember, this is the square root of, well, it's the square root of the first standard deviation squared, so 0.3 squared, over the number of people in the sample. In this case, we had 36 cars, plus the second standard deviation squared over the number of cars in that sample, which is 41 cars. So that ends up being equal to 0.08. Put that 0.08 in there. This is my z-score. And so my z-score in this case is equal to 0.1 or 0.08, which is equal to negative 1.25. So let's say negative 1 right there. Negative 1.25. I looked that up on the table, and I get 0.1075. The question is, all right, so for that null hypothesis and the alternative hypothesis, remember that the alternative hypothesis was less than 0. So we're looking for the area to the left. So this is actually our p-value. Our p-value in this case is bigger than our level of significance. So it's bigger than our alpha, so we fail to reject. So this is totally possible that we run into a sample like this, where it actually shows that the other car, in this particular sample, shows that the other car has a smaller miles per gallon. But that's, or actually I guess it has a larger miles per gallon, but that's okay. We fail to reject in this particular instance.